Hi there, I'm Joshua Pulsipher, and I'm a new assistant professor here at the University of Waterloo in chemical engineering. My group's research focuses on developing techniques to help us navigate the complexities that come with decision-making over large-scale systems, especially ones that are subjected to the uncertainties that surround us by just living in this world. And the decisions made in these applications have significant implications in terms of sustainability, profitability, safety, etc. So for instance, let's consider wildfires. Firefighters face all kinds of complexities, especially as this becomes an ever-growing issue in Canada and just the world more generally, as they have to proactively think about what areas of land they should treat and where they should allocate the resources to be more able to respond to wildfires in a more proactive and effective manner. In fact, there's an infinite number of choices they could end up making as they decide this, as there's a continuum of where they could end up putting things around on land and such. So how do they make that decision out, and what can we do to make the best decision? Well, we could try to use some modeling and simulation techniques to simulate every possible choice they can make. There's an infinite number of those, so maybe if we just simulated a whole bunch of them, by the time we found a solution that was pretty good, wildfires probably happened, damage is done, we took too long. But luckily there's a better way. Optimization provides us a mathematical toolbox to help us traverse that landscape of complexities and help us find policies that are maximally effective without having to enumerate every possible choice we can make and guess and check to see if it's good. So what my group does is we develop optimization methods, particularly ones having to do with phenomena over space-time, to help us make maximally effective policies. We also leverage state-of-the-art machine learning tools and models to help us capture systems that can't be completely characterized by first principles. So going back to wildfires, for instance, this is a great example, as they include all kinds of complexities, from complex reaction and diffusion mechanisms, and as they interplay and are affected by the weather and by a variety of other factors, such that it's very difficult to model those, for one, and even more difficult beyond to even optimize them. So the tools that my group is coming up with can help enable firefighters then, with this complex phenomena, to come up with maximally effective policies such that they can mitigate and proactively deal with this wildfire risk that we face increasingly more now with climate change. What's also great about the methods and the advancements my group comes up with is they're general. They don't only apply to wildfires, but they can apply to a whole range of important things for society. So for instance, they could help us figure out a way that has minimal emissions, or net zero carbon is the term people typically use, for an energy system across Canada and the world that's more effective. It can help us come up with more sustainable manufacturing practices. It can help us identify a more sustainable supply chain and resilient supply chain for future pandemics, and inspire the next generation of effective self-driving cars. And all of this, I leverage my background in open source software development to come up with accessible tools such that practitioners in these different fields can actually take these innovative methods we come up with and actually use them and make impact in their fields. Hence, the work that my group works on in machine learning and optimization empowers decision makers across their different diverse areas to make much more effective decisions and navigate the complexities they face, such that we can engineer the world for more sustainable and a happier tomorrow, essentially. Thank you.